Valve selection basics. What is an actuator? In industrial processes, control valves regulate flow, pressure, temperature, and level, ensuring systems operate safely, efficiently, and reliably. But a control valve cannot move on its own. That's where the actuator comes in. An actuator is the component of a control valve that provides the force and motion required to position the valve. More specifically, an actuator is any device mounted on a valve that, in response to a signal, automatically moves the valve to the required position using an external power source. In a control loop, the controller sends a signal based on process conditions like flow, pressure, temperature, or level, and the actuator converts that signal into mechanical motion. That motion moves the valve stem or shaft, changing the position of the internal flow controlling element and regulating the process. In simple terms, the actuator is what transforms a valve from a passive component into an active, automated control device. Why actuators matter? In modern process systems, conditions are constantly changing, and the valve must respond quickly and accurately. The actuator determines how fast the valve responds, how precisely it positions, and how much force or torque it can deliver. Actuator performance directly impacts control accuracy, stability, and reliability. For example, actuator design affects rangeability, the ability of a valve to control both large and very small flows. Even a properly sized valve cannot perform well if the actuator is not correctly selected. Primary actuator classifications. Actuators are first classified by their power source. Pneumatic actuators use compressed air and are the most common due to their reliability, speed, and cost-effectiveness. Electric actuators use motors to provide motion and offer high precision and stability, especially in remote or utility-limited applications. Hydraulic actuators use pressurized fluid and are ideal for high-force, high-speed, or safety-critical applications. Each technology has advantages depending on the application, environment, and performance requirements. Actuators are also classified by the type of motion they produce. Linear actuators move the valve stem in a straight line and are used with globe and other sliding stem valves. Rotary actuators rotate a shaft, typically 90 degrees, and are used with ball, butterfly, and plug valves. The actuator must match the valve's motion for proper operation. Common pneumatic designs. Diaphragm actuators use air pressure acting on a flexible diaphragm to move the valve. They are simple, cost-effective, quick responding. However, they are limited in thrust capability, stroke length, stiffness, and control precision. These limitations can affect performance in demanding control applications. Piston-cylinder actuators use pressurized air acting on a piston to generate motion. Compared to diaphragm designs, they provide higher thrust, faster stroking speeds, greater stiffness, more accurate and stable positioning. This results in improved control performance, minimal hysteresis, and excellent linearity. A simple way to understand the difference is to think about pulling a stick out of the mud. Imagine a small child trying to pull that stick out. They have to use all their strength, pulling and yanking, until the stick finally breaks free. And when it does, the sudden release causes them to lose control and fall backward. Now imagine an adult doing the same thing. They have the strength and control to pull the stick out and reinsert it smoothly, without overshooting or losing balance. That's the difference between a diaphragm actuator and a piston-cylinder actuator. The diaphragm actuator is like the child, limited in force and control and prone to instability when overcoming resistance. The piston-cylinder actuator is like the adult, powerful, stable, and precise, able to move and control the valve smoothly across the entire stroke. For applications requiring higher thrust, better stability, and tighter control, piston-cylinder actuators provide a clear performance advantage. For rotary valves, common actuator designs include rotary piston actuator, rack and pinion, rack and gear, and scotch yoke actuators. Rotary piston designs offer long life cycles and precise control for critical applications. Rack and pinion designs are compact and cost-effective, suitable for both on-off and modulating service. Rack and gear actuators offer high precision and durability, making them excellent for throttling control. Scotch yoke actuators are designed for high torque and are ideal for large valves and emergency shutdown systems. These designs convert linear piston motion into rotational output for valve operation. A control valve is only as effective as its actuator. The actuator must be properly selected based on required force or torque, speed of response, control accuracy, and process conditions. In practice, actuator selection is a critical part of valve selection and directly impacts performance, reliability, and life cycle cost. At Trimteck, we engineer and supply complete control valve solutions, including actuators tailored to your specific application. Whether pneumatic, electric, or hydraulic, linear or rotary, general or severe service, our goal is simple: deliver precise, reliable control for your process. Visit trimteck.com to learn more or reach out to our engineering team for help on your next application. And don't forget to like, subscribe, and click the bell for more valve selection basics.